Okay, this time. Okay, so last time we talked about the last time the first half of the lecture was more simple. And anyway, so let's review this. So we start talking about superconductivity. So superconducting state is a coherent state of the so this means that this means that superconductivity of the vacuum and then dk c so it's coherent between if you can so it's a coherent superposition of the vacuum and then the superpair. Both so CK and superpair is the anyway, so if you have momentum space, the frequency for momentum there is a moment here and another place in the so they form the superpair. And somehow the BTS grounded is some superposition between. So it means that the superpair is created and then annihilated in this the BTS state. So this is confounded state of the superpair. So in the condensation of so in the vacuum, so you just forget that the superpairs and then superpairs. And also we consider that from a tunnel feature this form. First of all, I didn't mention it. So CK is the remember CK, what is the CK is? Definition of CK. So it's from K from the primary energy. Essentially so this is the C diameter and G is the one. Number density. Number density and the energy, measure from Fermi energy is the kinetic term. So that's the kinetic term, and this is the interaction term. And of course, the long one, second lecture of our class. So we learned that the H interaction term is something like in the that's what we learned. The previous thing, so we just write down like this. And if you do the full transformation, moment of space, so this will become E of Q, sum of Q. Oh, sorry, C. So in the previously we learned long time. Yeah, it was the second lecture in the second conduction case. And here, what we learned is that it's so essentially what we have is you have a pen, and here is this way. Okay. Q plus Q. And alpha pin, became a Q. What's the interaction? So this Hamiltonian, the interaction Hamiltonian can be written as this polygon diagram. Okay. So that's what we learned on the previous page. Here, of course, we take the everything to the S way. So here, interaction is the S way. Means the total momentum. Equal to 0 and also total angular momentum is also. So we have a spin up, spin down, so equal number in here. Therefore, in total, it's a spin thing. Is it okay? And then we use this one to that. So here, so we use the repeat approximation. So we need the approximation is equal to I or J is something like that. Or J. I mean, I'm doing very typical or J. Okay. And this can be written as I or J, and then plus I minus I or J, and then that's the opposite. So, and then quadratic term we know. So the fluctuation is very small. So we assume the fluctuation is very small. So essentially speaking, so we have a long term, but quadratic term fluctuation. So it's a mean field value, so the expectation value, and it's a deviation. So if deviation is small, it's quadratic, so we just ignore this is equal to 0. And then, so we have OI and the expression value OI and the expression OJ and also expression value, and just get rid of the concept of remove. We get this. And we try to diagonalize this Hamiltonian by using this volume or volume. Do you know Bulgarian nationality of Napoleon? Russian, or maybe currently disbalanced with Ukraine. And okay, Soviet Union. Anyway. Okay. then try to just diagonalize this one, and then yeah. So after diagonalization, so here, so we assume this EK prime is less than divided, less than divided. So essentially, so what we assume is that the Cooper pair is due to attract. Oh yeah, I have to mention this negative sign is here. Negative sign is this attractive form. And here I use E of Q is constant. E of Q is constant to do. It's independent of Q. It's Q. So that's what I am. Okay, that's it. Then we try to diagonalize this one, then H is literally and the other, okay, and plus unequal function. Maybe sorry. And then yeah. And EA is given by square root. So note that here, AKA is something like UK, DK, DK minus DK, and it's DK. So this is more like an electron-like excitation, like excitation, and this is called Hall excitation. Excitation. So we consider some very thin shell around the Fermi energy, so here. Okay, so this wood is less than the Y energy, less than H bar omega t. And then we consider that around the Fermi speed, some group here will be called the bound state. And then if you create some state in here, creating a, I just wrote that up, red dot here is more like a, so if you create a state around here, it's more like a distance. So it will be achieved by the equation operator. But in this guy, maybe I use yellow. It's something like this. So you get rid of some state from here. So that is more like a whole excitation. So you just get rid of some energy from this nation. So from this is more like so this AK is more like a quantum. So it's not particle. So but really, so if you diagonalize system, so it's better to in superconductive detail times one here. To diagonalize, it's better to use A and B as a equation and other operator. So AK and BK is the equation for pattern. It's the equation another operator. Operator of the quasi-particle phase. So the quasi-particle state is the combination of electron-like excitation and then Hall-like excitation. So it's very some like a mysterious I mean, from the viewpoint of this, the previous phase. And we look at the dependence of this delta by the temperature. Temperature dependence. Last time, delta of T of this. Oh, so another question is that maybe I didn't before going to so another question is that why we can split so when you consider Cooper pairs, Cooper's problem there. So we assume the infinitesimal, infinite attraction, attractive potential to form the bound state of it. So, but I mean, of course, so you have all, you have electromagnetic repulsion due to, I mean, if you consider fermion or two electrons, they follow each other via Coulomb forces, but we assume that attractive potential. So that's why this assumption is valid is that because in the so in the metal, so this is valid. So this is valid because in the metal, so this is Coulomb repulsion is spring. Due to the the metal line, so we can ignore the Coulomb repulsion. And also, so here, so that was number one. So number two, you have a final mediation. Attraction. So because I mean, you have a lattice, and if you the relation that if you have a lattice many times of the nuclei, like a glass. And if you have an electron here and the lattice is solid, and then the net charge you can put positive, and another electric charges will be attractive, and so that is called phonon-mediated attractive forces. Actually, this one is actually win against this big critical result. So that's why you can in this one attractive force. That's the one. Okay, anyway, so then we assume this BCS Hamiltonian and try to see the delta is essentially delta is the expectation value of this EK. And sum over like this. And what we saw is something like this one. And then here down the notes. So this is equal to 0. And we derived this using the Fermi statistic. We derived delta naught is equal to divided by the critical temperature. Sorry. Roughly, sorry. Sorry. Yeah, E to the 1 over G, or the number, minus roughly. For G is given by G0 times density of the density of the permeation. So that's and here, so you can assume that, so this is not equivalent, fundamental, and the ultimate. Okay, and also, so EC can be written as 1.13 H divided E to the minus 4 average. Okay. So like this. So that's what we derive. So this crystal temperature also can be written. It just E to the minus 1 average. So roughly speaking, the order, so we have to be. And also, so that's what we derived last time. So the derivation is I already did, I'm not going to repeat. And also with using invention notes, I'm not doing it. So you can think of it. You can pull that off. So now the thing is that so around here, behavior, how does the behavior look like? Around here, how behavior look like? So T, but the T is so the behavior. So we have derived that this behavior around here is the of the double square is proportional to T minus Dt, Dt minus Dt divided by. So therefore, here around here, so delta is proportional to Dt. What we have derived last time. Is some of your question. Any questions at this moment? Okay. So then we consider about something called the Vitalik ring function, spectral function. So Vitalik ring function is equal to like this. So Vitalik ring function and the spectral function is something proportional to imaginary part of a Vitalik ring function. But we already saw long time ago. Okay. So we start looking at this one in the ring function. And then maybe we started to repeat the calculation. So for instance, in upstate of a retired gain function K, like this way, is you just go to momentum state. Like this way, and perform where you go for transformation. Where you go for transformation. You get to use this curve. E and and also into curve. Like this. And then you use the fact that the Hamiltonian is diagonal in this. So AK is E divided by EK, E divided by H bar, and the AK is the time evolution is governed by integral operator. And then here, AK is the, but the particle is the, that is, this creation of non-rational down on Hamiltonian calculation. And then we derive that the, so vector function. Another part. But we get that's what we have. And the spectral function is exactly the let's do some density of state with K. It's something like after EK, you got the delta function minus EK, you got the delta function. The weight you get curve, so you have you proportionally get curve, and this is EK curve. So that's what we have. So weight of density of state. So this is for like an electron like excitation. So this can go to the whole like excitation. Okay. And then, so you get here, I should write it down. So you get current is equal to 1. Okay. This is integral up from to k equal Alright, so you can check this one. The U square is equal to so is equal to what? You can check. Yeah, so this is exactly what you can see from this picture. So you have the decay dagger, which just creates an electron on the thin shell near the frequency, and the whole like excitation just get removed the such a state from the remove such a state from the easiest one. That's what really happens. Question? Like this one? Okay. Okay, now so we will try to derive the density of states in energy and the sum of k from k to and then this can be done by just using and this can be done. We're just looking at the D here. And then infinity, we need C on the top. And you want plus D in square plus some square plus like this. So we only look at this part. We only look at this part. And then forget about this one because we only look at the positive energy part. So we first compute the equation of we consider. Then we just integrate over this thing. We do over this here. We go here. We go to so yeah, k is given by like this. Integral over here. And then so you notice that this, so from infinity to infinity, this odd function would the integral odd function is here. Odd function is here. So just ignore it. So this is something that is here. And then replace this term which equals to fraction down. Then what we get is like this. And that's how we derive the equation. But this is beautiful. So, and you can do a similar calculation for the whole like excitation. So then you can be done. Yeah, by the way, so I didn't write. So this is E and next dk. So you have delta zero here and delta zero here. No, so it depends on that. It depends on temperature. And the impact is something like that. And then you behave like this. Like this. That's causing when all the states. So you can see that the yeah, this is more like a E equal to not E. And this is E equal to I think it is about that of the image. Oh, I think I shouldn't be right. Okay. And if you consider E is less than, so this is minus. So this is electron-like excitation. Excitation. This is Hall-like excitation. Hall-like excitation. For this in a way, E is the minus the other or side. In the case of this one, you can just drop the sign and so on. So therefore, it's the same calculation you can do. So therefore, if you write down, so this is equal to E. So E minus delta, and D of E is more like this one. So then the extent becomes like this. So if you go to the delta, the number of states becomes higher. And if you go to like close to the delta, number of states goes up. But if you change the energy to high energy or negative high energy, then the density of state will just decrease. So namely that here our term C is contained D is equal to 0 around this in this region. So in this region, D is just simply 0. And suddenly, the number of states become huge when the E is close to 40 for the detailed theory. And this is experimental. The 5 DCS can obtain the normal curve in 1975. So that's a density of set. So the reason why I talk about the reductive function and so on is to derive this density of states from spectral function. So spectral function, if you sum over the spectral function over the momentum, we can just get the density of states dependence on the density of energy. And you can. So that's how we use reductive green function or green function to obtain the data. So rho is essentially minus 1 over pi is imaginary of the CR. So this one we derived like a 3 or 4 lecture before. So that this relation is very useful to obtain this density with respect to energy. Any questions or comments? Oh, sorry. So this is not 0. Actually, this is the sorry. This is not 0. So this is actually D0. So 0 is here. I think this is 3 right. So this is the D0. Okay. Any questions at this moment? Now I'm going to derive solution capacity. So in superconductivity state, the heat capacity is the most important. As I mentioned, the long time. So this is first experimental of the for the superconducting state. So long time ago. So I don't remember the year. When was that? 9? Like a beginning of 20th century, or maybe. Anyway, so yeah. So this is it. So that's super. So this is the how the part superconducting state from the experimental side, and we try to derive this one by the detail theory. So the form of the heat capacity is just the derivative of entropy with respect to temperature. Okay? Okay? With respect to temperature. And then S is given by what we already know this is equal to some over I, and the part is I log of n plus I, and plus 1 minus n epsilon I. I have 1 minus n epsilon I. Yes. No, sorry. The entropy is not. So L bar is the so number density operator. Expectation of battle. Number density. Or distribution function. function. So distribution function. And in this case, we will use the Fermi statistic. Okay. And then for the original, we have the partial excitation is the plus minus b from k. So this can be adjusted as minus 2 times k. Okay. And plus k log of n bar. Okay. So now we will perform the derivative with respect to temperature. Okay. So this one is equal to now, we can write down minus 2k b sum over k b and bar and bar log and bar plus 1 minus n bar log n bar times d n bar d dp where d is just defined of delta c. That's fine. Okay, this derivation kind of cumbersome. It's I just write under one line because if I write everything, it's going to be horrendous. Okay. So suppose okay, what is n bar? N bar is equal to 1 over e to e plus 1. Okay. So this is Fermi-Dirac statistic distribution function. Okay, distribution function. Okay, and then that's what we have. Fine. So we can do, let's call this one. I mean, the derivation is really takes time. Okay. So let's call this one F. Let's call it. It takes a lot of time to do it. So EF, E and R. So that's first term is given by log and bar log 1, and then minus log 1 minus n bar plus 1, which is the log n bar 1 plus n bar. Okay, so that's what's happening. And like this one you here, this is in fact equal to 1 over EC plus 1 divided by EC divided by EC plus 1, which is equal to minus C. Is it okay? Is it okay? Okay. Okay, and then D is equal to this one, right? So D is equal to this one. So now for C is equal to 2 times sum over K. D and bar into D where K is. Okay. Israel or what? And then what we need to do is that the and then the bottom of K is equal to ESI dP. So this means that the ESI dP is equal to KE and dog okay. 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 1.37. And then and also dP over dt is equal to del beta del P depends on beta del dk del T and T is equal to this is equal to minus term dk and then this is equal to beta 1 over 2 dk. So note that dk is equal to the plus delta like this. Okay, so that sounds really okay, so far. Okay, then plug this one back into here. Back into here, then just this one is equal to yeah, sum over K, dk without alpha, dk, and if you just the massage equation, you get the minus dk. Whatever, you can eat, okay, without further eating. That's what it is. Okay, and then if you just attach this equation, you know, then that this is equal to, so this is equal to, so this is equal to P over T. You just attach the equation, okay? And one is there, then one, okay? Minus P over 2 del squared dt. Okay. So that's what I did. Equal 2. And then that's what written in the second equation. Okay. That's a heat cap. Okay. And then when the t equals to t is greater than t, then delta is equal to t. So you can ignore this term. You can ignore this term, and of course the happen is that the Um, so, okay. T is equal to 1 2 over T, sum over K, and minus down hand bar, that's EK. So EK, and the EK in fact is equal to so now the equal to 0. So this means that the EK is equal to TK. EK, EK. Okay, and then you can just write down this is P, PK, and this is PK. Okay. And then here we just replace the function to P, D is from DP, and then minus down and bar, down CK, and then, sorry, maybe. C and C, everything C. So this is just the state. Okay. And C is good. We can just write down like this. Okay. So now, in the lecture, I made all those derivations. So I just write down very anyway. But because I don't want to write down all of the derivation to the lecture on them, and then it's just a legal algorithm. And then you can just continue. So the permit, so T of C is roughly T of T. You can just write down like this. It's all so therefore D is equal to, sorry, T, sorry. T is equal to over T. T is so permit energy, and I think it's C minus N bar. And now recall that bar is equal to 1 over E to the C plus 1. We are going to here, and this is equal to C times over D is from F. And then, so therefore, N bar del C is equal to beta times E to the beta C and E to the beta C plus 1. And this is equal to sum of wash. And this is equal to beta over 4 plus wash. Beta C over 2. And plug that into here. And this is equal to infinity to minus infinity is divided by beta squared x over 4 times wash x over 3. Okay. And this is equal to log P E of F beta squared. And then, so if you do the formula integral, this is equal to pi squared over Q. So from here, we'll conclude that this is 2 pi squared divided by 3 E F and equation 30. That's what I do. What I have written in the actions. Okay, so you have to do lots of calculation. Do you understand? Is it okay? I mean, here, so you have to redefine x t to x by 10 by beta. And that is the measuring. It's one of the. Okay. So now, So here's the dimension. So delta behaves like this, delta and then T like this. So this would be P, delta naught, and then this would be. And now we are interested in what's going to happen. Just fit around here. Just fit around the temperature group. Can I do this quick one? Yeah. So when T goes to 0, what's going to happen? So that delta T roughly delta naught. Delta naught I already did derive by using divide the shape of the e to the minus 1 over g or something like that. And also T over 2 delta square over g is negligible. It's negligible EPS square. Okay. It's the exponential small, independent exponential small. So that therefore this one is equal again. Yeah, it's going to be a horrendous calculation. Okay, but okay, let's do that. So this is only one time. So the only person who attempted that all of you can anyway. The roughly speaking, T over T, sum over K, is the same calculation. EK, EK. Okay. So now we can now simply define that EK is equal to square root of P squared plus delta naught. That's what we're doing. Okay, and then again we replace by sum over momentum by using density function. And this is equal to F over T and then minus infinity to infinity is T minus half and half. And we assume since the integral is even, so integral is even. Is B. So then maybe I should do here. Okay, so therefore this is equal to 4 times the Fermi energy E from 0 to infinity in C minus the half E and the current 5. And we already know that the distance. Yeah, and now is equal to beta times 4 push square beta E divided by 2. So that's what we get. So now, so when t is very small, t is small, almost, so t is greater. So c is epsilon j minus j minus e, and this is very small. So, I mean, epsilon k is from this is the Fermi machine. Fermi machine now, it can be treated as very small. So therefore, so you can assume this one is roughly speaking. So E is roughly speaking delta naught, and also beta E is much greater than 1 because the temperature is very small. Okay? So if you look at this one, so this can be, so in this approximation, one can just show that this is roughly speaking 1/4 E to the beta E. No, minus beta E. Sorry. So this is roughly speaking beta times E to the minus beta. So that's what we can. Plug down into here, then this is roughly equal to E to F and E 0 to infinity, E to C, and for beta. Okay, like this. Okay. And then, so we assume that E is roughly delta naught, so that the plug this one is out of the integral. Or beta dk is from or the T is shown minus beta delta square, delta square, and 0 to infinity is C. This is delta naught square E to the minus beta delta naught, and 0 to infinity E C E to the minus beta E square divided by delta naught. 2 delta naught. Like this. Like this. So that's the approximation. So here, so again, E is like this way. So this I approximate like this way. Delta naught plus so delta naught, so it becomes whatever. Yeah. Plus C delta naught square, right? This is delta naught whatever plus E and delta naught divided by the C. That's what I do. And it becomes like this. And it's a Gaussian, so then you can perform. And if you perform it, then the Gaussian integral and this one is equal to 4 beta. Okay. And then in my lecture notes, I just written down for this is equal to. Yeah, so that I press all the calculation like this one in the lecture notes. So this one is equal to. Yeah. Take the issue. 1000/5. Thank you. That's the lecture. Okay. Okay, what are the physical interpretation of this equation? Is that the here this is, so here is the exponential suppress factor. Suppress specific in here in this term. Then in addition to that, there is some power law term. So yeah, so this is power law term. Power law term. This is coming from the from three-dimensional phase space. So it's just coming from the Gaussian integral. Based on space and space, and then near minimum of yield. Okay. So that's how you do it. Okay. Okay, and then so what's really happening in the form? And then the sequence. Unfortunately, it's stupid in relation form. So the T represents T. T is like something times T. Okay, anyway, it becomes linear. That's very natural in terms of quantity. So it becomes linear after T is equal. Okay. And then first it becomes especially suppressed, but suddenly become like this way. It behave like this. So this is T of T, and this is T. So okay, let's call gamma T, and then here we have the gamma T. Okay. And you can show that the D curve dt is equal to so as I mentioned, Dallas curve it behaves like an H varies per kd. The thing is curve divided 7 times the hair 3 is d minus t divided by around the t is less than t, so t is roughly. That's I already showed before. Therefore, you can do the derivative with respect to t, and then this is equal to this is equal to after t is equal to minus 8 per km. kb per tp 7 layers. And this is roughly, I don't care the 1.43 gamma. Sorry. So no, that's not this. So not this. So this one. And then you can, from here, one can compute the difference between this and this, the opposite. And this is equal to roughly 1.43 times gamma T. So if you compute the, so C is equal to 2 over T and 1 over K, dk squared, minus T over 2, d delta squared divided by dt times minus and half down dt. So that's what we show. And using this derivative of the delta squared with respect to t, one can compute the speed at the, if you approach from here, from temperature lower than the critical temperature and then approach from here to the PC. So one can compute delta C from top to bottom here. So this point is just you just compute it from right side of the diagram, and this point is computed by left side of the diagram. Okay, and then take a limit to t equals to tc. So one can compute delta c and then delta like this. I mean, from right hand side, I assume this is equal to t. Okay. From left, if you compute from left, you have to use this equation. Okay. Then one can compute the gap of specific P at the critical temperature. And then one can compute it. Okay, that's what will happen. And then this is this is already observed in the experiment. Okay, that's and you can compute entropy by just calculating. So just integrate over. due to T like this way. And then, so if you compute this one, so one can show like this one. So it's a little bit different. Okay. Of course, at the temperature 0, entropy needs to be 0. But the growth of the temperature is just lower than the ordinary value. That's one. Okay. Okay. I think fine. Okay, let's stop here. And take a break. So these are behave. Anyway, so this is linear. So this is normal state. This is superconductor. Oh my goodness. Oh my goodness. Anyway. Okay. Superconductor is something like this. Is it? I don't know. Is it different? Superconductor. Is it different? In Chinese? Gaming. Anyway. Let's not go. Let's take a break. Oh my God. Of course. Exactly. Is it different? Yeah. Oh, it's different. Okay. Oh, without taken. Yeah. Oh, okay. Oh, okay. So there is.画到最后就是那个。这两个例子应该都是就是就是有当两条你这个是，这俩就是有两方都会凑合。它最后一个不。电疗。我们的
区分刚刚区分就是有重复基本上都把它求和，没有就那是个流调。一般最高次的空间它会要区分上下指标法。有可能会按有一的情况，按情况啊，可能做一个那我没教过，我还没蛮快的就完。理解。哦，对，他连对流水房这个这个，哦，对的，其实到但是意识到它要它很多个机器的话，我就觉得，然后我回家之后，然后我就去做就看。我觉得很多我也这样做，当然可以，这是干钱，干钱。过去我们用这个什么反馈资源，都是这种灵活的方法，交流。这就是这样的，全看我的。反正怎么样？那个是我能把变成给他的我怎么说话？这就变成把。Other point that you make this but this is without I don't know. This should depend on the Yeah, back in the cherry, you can find roll part that should depend. So the ground can come from. Yeah, what's the gap equation? Size. What are the gap equation? Yeah. We need to solve it. 协议。
Okay, shall we begin? Okay, now, so we introduced the Hamiltonian. In Hamiltonian, shall we introduce the magnetic field or electromagnetic field? So we have the superconductivity, so whatever. We have a superconducting material, you have Meissner effect. So this. So Meissner effect. Okay. So Meissner effect. Oh, good. Okay. So all like that. Energy behavior in low temperature of this superconducting material. You have to use really quantum mechanics or statistical mechanics, very, very nice mark to describe this phenomenon. But somehow the details miraculously describe superconducting, the behavior, physical behavior of the superconducting material. Okay, so superconductivity is kind of like the detailed theory is some kind of achievement of like a trick of the statistical mechanics and quantum theory to describe the nature of the superconductivity. When you learn the quantum mechanics, you feel like somehow like feel weird or strange, like particle become wave and whatever. But it's just that's how the quantum system behaves. Like if you just, it cannot be described as classical mechanics. But if you go to low temperature and so on, so you encounter more exotic phenomena like superconductivity, fluid, or water interconnected, and so on. All those like a very, very strange phenomena can be only described by using combination of the quantum theory and statistical mechanics. So that's what I want you to feel. So those are really simple of the theoretical component. And then also those are confirmed by experiments. So it's a combination of experiment and theory. So that's kind of exciting areas. And the other exciting phenomenon we can explain is the Meissner effect. So to do that, so you have to introduce magnetic field in Hamiltonian. So if we know that Hamiltonian, we can just write down Hamiltonian in the presence of the magnetic field. We just have like this. Hamiltonian can be written like this. And then showing the equation is of course looking like this one. And then you can just charge density can be written and the current is given by this one you learn in the quantum mechanics. You should learn. So that's charge density. And this is current. Current density. And they satisfy observation. Okay, so start. Okay. And you can just promote this one into hidden conservation. So we can so the okay, so the second conservation. Yeah. 第一个对它当然这个 conservation we are fix this currency of the operator. M sigma sine sigma now sine sigma R and R. Wow. 哎呦。Like this. Okay, so we treated everything, all the field on the operator. Operator. And we all the system. So we call this part J of P R. This will be equal to J of D R. And then move on. Okay. The expectation value of J of D is because the distance is equal to minus E curve over M. And what's this?
Yes.
Number density. We have to sum of all states. Number density, sum of all states is equal to 1. Now, well, this is just a so this is not surprising. And then okay, and then J of P is again J of P is equal to P. J of P. Oh, sorry, I have to mention this is P. P coming from paramagnetic current. And this E is diamagnetic. So this in chat is, I don't know. And the most likely, I don't know, most likely this is Chinese. Is it famous? Is it? Yeah. 我这个智商检查到我。 Yes. In Chinese, no, in Chinese, how is it written? Of course, current is something like E. Oh my goodness, something E. It's horrible. My brain's already. Yeah. And anyway, so that's in Japanese, so I'm not sure in Chinese anyway. But you can understand what you mean from the and anyway, so the P and D level does E and then I E H1 M B. Oh, sorry. So the Fourier transformation DQR JPR EIQ. That's what I want. Minus 1. And this one. And we also use this style sigma of R is one of the current P, the sum of CK E to obviously R, and it's the segment, and then you can do like this, okay? Like this way, and then that is the same, and then you plug that one into here. What you get is that the EH bar and B, and this one is sigma, and E Q R, again from up to the right, and then okay, that's what you get. And if you perform the R integral in the Fourier mode in participants, we can just write down our digits. Okay. Divided by M, D, and 7 D Kevin cubed, and 6. Okay, that's what I mean. Okay. Okay. And here, so here K is roughly the K of fractional momentum, and so this is roughly the inverse of lattice spacing. Say lattice spacing L is the lattice spacing of the superconducting material. Conducting material. Okay. Metal. However, Q is the roughly the whatever wavelength of magnetic field of magnetic field. It's macroscopic magnetic. Yes. Okay. So this is, of course, this is the microscopic. Then the macroscopic. One. Japanese. Maybe seven. Anyway. Even if it's not the same, you can. Okay. So the output, you can assume that the K is much greater than Q. So that here you can assume that the difference roughly minus E. Okay. Maybe I can put that J of Q of P is independent of Q. Okay. Okay. So now, you can define the Hamiltonian is something like the sum of sigma dqr by diagonal of sigma of r, and then minus h double square plus a e, and then square divided by 2 minus mu and phi sigma of r IO and b. Okay. And this is in fact h ECS minus dqr a of r dot j dot e of r plus order s squared. Okay. So yeah. So this part is roughly what's happening with the h number squared by 2m minus b beside under side part plus b integral sum of so of course b is something like we already saw. It's a minus b0 sum over c daga c or something like that. Roughly in a momentum space. Okay. Long story short, so let's write down this one. Is a momentum space. This is whatever b, sum over q, a minus q, and p of a. Okay. And this is equal to so this is equal to, long story short, we're not going to derive everything. So CK dagger up, CK up, E, and then E to the H bar, K dot Q divided by MB, E H bar, K dot Q, and B, and then CK up, CK dagger, like this. Increase that. Okay, the derivation is not so difficult, so I'm not going to repeat. If you want, you can just take a look. Okay. And then from CK dimension C dagger and C to A and B. So that's what we are going to use. And then so this one is in fact equal to sum over K E H power K dot N Q divided by N C K dagger K dagger is some of. And I will ignore, so the constant ignore. I will ignore constant. Okay. So therefore, so it's for Hamiltonian. It's sum of K, K, sum. This is mine. Plus so it becomes like, oh, sorry, I didn't use one. So EK, so this is coming from HBC and ECN. This is coming from HBC. Okay. Yes, that's how you modify it, and how you modify the HV. It is Hamiltonian in the presence of the electromagnetic field. So you just insert plus this term and minus this term in front of A and B. So which means that the quasi-particle of A just is along. You can just have along the vector potential or whatever electromagnetic field, but you have a negative sign, the opposite for the B quasi-particle. Okay. So now, what we are interested in is that we just want to have J of P. So Q, expectation value of this. And this time, very easy, sum over, now very easy. Sum over K. like this. Okay. So this one you can just, and how we know, so this is the distribution function for this quadriparticle, okay? This is distribution function quadriparticle. So we already know this one is the, has the energy of this. So alpha 16.3 and above EK plus this quantity. EK Q divided by P, and this one is the environment. And of course, it's also E to the x so we can mu plus 1. Okay. And then looking at the leading order of this one, is some constant. I don't get it. Okay, cancel A, Q, and the minus B and 1. B. Okay. And then plus all everything. Okay. And then, so if you look at this, this sum over x, and then, okay. And if you look at the x component of this current, x component, and then this one is the x component times k dot aq minus b above dt plus over. And here, so you just replace the integral of dq k to pi to q function different. Then if this integral only survives the even integral in terms of k. But here, if you expand this one, if you expand this one, this one is equal to kx, aq, ax plus ky, plus kb, and I already suppressed the q. For now, so the only even part is kx, ax. This is even, but these are odd integral. These are odd integral. So therefore, you can ignore this odd integral part and just looking at the even integral part. Okay, and then now for this one can be written as some number times the dq q is first. Okay. Fine. That's what we will do. And then combine the previous part J of Q is equal to J of this paramagnetic part, and then diamagnetic part, and this can be written something like minus n of E divided by E squared over n proportionally, where this ns over t is equal to 1.41 n if you can keep my h bar k product divided by 3m minus dn of e. Okay, so that's solution. So and this magnetic equation is for global images. So this one comes from J of D. And this one comes from J of D. So here at the end, so this integral really is just rewriting of this part. Rewriting this part. And the one just coming from this diagonal part, which is okay. So this normal equations are key to derive the maximum effect. But normal equations before the BC action, So this is the this can be it just current is proportional to magnetic the electron to A. So this one, I mean, it's easy to derive up to some point. Okay. The important part is that so ECS can be derived and S by microscope. That's what okay, and then this P and if we behave like this thing, and then this P, this is M. Okay. And then T equals to so N. So here N is the number of state in momentum space. Momentum. Oh no, it's just number state of the yeah. conservation of system. At T equals 0, I think T equals 0. Okay. So this means that the here's the equation. So here means that the T equals 0, this is equal to this part. So this parallel magnetic current contribution is here. So T equals to, so this means that the T equals to 0. The contribution is only from J of B, J of B. And then E equals to T, JD contribution cancel, or JP contribution cancel with the J of D. So the NS becomes D. So it becomes simply 1 minus 1 equal 1. That's what I mean. So to the point is called 强制性，这是反制性。自行。Okay. Okay, and then we can derive this and its behavior. Complicated. Okay, before deriving, yeah, I think if I derive this behavior by integration, it will take time. So before deriving this integral, evaluate this integral. Before evaluating this integral, let's go to math. Way more eliminating physics and lighting physics. So we have the local equation J equal to minus NS squared divided by M. Like this way. And then from the electromagnetic equation, the output J equal to minus NS squared plus M, the output N, and then this equation M squared divided by M, and B. Fine, but Maxwell equation tells you that the so if you use the Maxwell equation, this is equal to 1 over mu 0, nabla plus nabla plus E, and then which is equal to 1 over mu 0 nabla dot P minus nabla squared. And then using Maxwell equation, this is equal to minus 1 over mu 0 nabla squared. This is 0 due to Maxwell equation. Therefore, okay. So from here, one can show that the lambda square of B, 1 over lambda square B, now is equal to the square root like this. Okay. And we can solve this equation near the superconducting material. Suppose we have the B is something like a 0, 0, 0. So in the on G field, and X is like here and 0, and from here superconducting material. So and this is the vacuum is like this. And then so the magnetic field is in this direction. Okay. It's this direction. This direction. Then we can solve the equation. To solve the equation, so d is going to be c divided by d squared. One of the lambda squared. Okay. And you can solve this equation so that the d of c at the boundary condition d of like this one. The solution yeah, I mean, here there are two solutions. One is the e to the x over lambda plus x over lambda minus x over lambda. But we import the solution, it does not diverge when you go to infinity. So that the only solution is the exponential decay. So this means that the anyway, so I lost the relationship. So if you have so there's a zero in some kind of a p, and then suddenly once you enter the superconductor it becomes exponential decay like this. So the amplitude of B field is just decay. For example, the magnetic field is spring inside the superconducting material. Okay. And then this lambda is called the London cancellation. And then iteration. Okay. And then so it's a proportional to lambda is like this way. Then its lambda is proportional to n s of t minus 1 half. So therefore it becomes like this. So which means that is somehow the final length in the final length for some temperature, but if you approach to the critical temperature, it becomes like a diversion, which means that it starts incorporating, reacting with the magnetic field inside the superconductor or inside the metal. Any questions on this one? So this means that the following. Physically, so what's really happening is that so if you have a superconducting material like this way, and then apply the magnetic field in like this way, but they create some current. So J, the longer equation is J is somehow inverse, so minus the proportional to K, which means that I think we should obey like this, right? So it just their current is proportional to minus the proportional, which means like this. So inside of superconductivity, this Cooper pair, we just create superconducting material is created J like this. That cancel is the magnetic field from the external magnetic field to cancel, so that this is J inside the superconducting material, so that you can screen the magnetic field. So that it becomes like this. And so if you have in this way, so you just have like the magnetic field is just counted off. Okay. So this is from my part. Any questions or comments? Okay, so now we can try to derive this quantity by just integrating in the rest of the number. Okay. So this one can be written as S of T is 1 and 4 over 3. So T is equal F infinity minus infinity E B T. I'm just rewriting this part by using the density function and see the energy from the initial problem. Okay, and then you can show that you can show that this quantity is the fact, the like 3n over 4. This is 3n over 4. That's I can show. So DE is in fact the proportional to the each from the one part of this 44. Long time ago. So long time ago when you learn the idea for permeance, so D of E is E to the one part. Then, so if you just solve this one to the EF, to the D of E, which I call it is equal to the EF of the theory, and this is proportional to E to the 0. What I try to shoot on the board. How hard you it? Sorry. Yeah, I forgot. Yeah. And this is equal to n over 2. N over 2. So if you just so number of state is divided by 2. 2 is coming from the spin degeneracy. Spin degeneracy state. And the integral for density from 0 to Fermi, you get the number of states. Okay? The number of states. And then this should be equal to. So this is the case. And then F times this from F is equal to 3 times 2 over D is from F. Okay. So is that okay? This is equal to okay. Let's suppose this is equal to number times. And this is equal to 0 is from F. Number plus is from half E, which is number times 2 over 3 from 3 half. Is that okay? And F right. Okay. And then this guy is just a number times E from F 3 half, right? Is it okay? Yes, is it okay? Yes, and if you want a field of half, you just count it, right? You just count the 2/3, and you get this. Okay? And we know that the D of it from F is this guy. And plug that into here, you get the D equal to 3n over. N is the number of states, and then 2 is the spin degeneracy. We have to do it anyway. Okay. So therefore, they count them, and let's okay. Now for And this is equal to minus infinity of d e and bar divided by dE. Like this. So the second equation can be just given shown as following. Sorry. So E is equal to I don't remember how so it's time. So dE and bar dE is something like A E to better that's one better me to better right? And then if you integrate over, and then E is something like this. And somehow it should become, if you do this integration, you should get one. I don't remember the detail. So you can approximate, sorry, let me do it now. So that you can approximate this is 3. If you do that, it's just minus infinity, infinity, E and about dE, infinity minus infinity, it's just sorry, but this if D is infinity, this becomes 0. So this is and about infinity minus and the minus infinity also in the number. So and y is something like E to the player B and C. So C. I don't need D. Plus 1. If C is infinity, this is 0, right? If you C minus infinity, this is 1, right? And then somehow it should get like that one. And somehow it should get minus 1.
Because you to minus
when find yes over the is so it's initial
Is it over 1? Oh my god. Okay. Yeah, I think it's okay. So this is minus. Yeah, yeah, yeah. And a minus. Yeah. And oh, sorry. So that's what it is. Okay, so this is equal to 1. Is it okay? Okay. Okay, so that's the case. And then now I'm running out of time. That's why I just derived the Einstein effect first. And then what I need to do, what I need to do is the NE and the bar E is equal to, I'm running out of time to 100 hours of variable E over 2 divided by, and plug that one into here and do a division. And you can find that also. Yeah. In some function times delta t divided by ke tc squared plus delta delta. If you plug this one into here, and it's just multiply the equation, and you get addition. Okay, so that's how we get it. So in particular, so when TE is around TC and T less than TC, we know this one is the this one is proportional to TC minus T. Now here actually it just go to, so if you go to the linear, it's just becomes linear degree. It becomes linear degree. That's what I want to say. Okay, let's stop here, and then next time, I think we'll talk about the Ginsburg-Randall theory viewpoint from the superconductivity. And after that, maybe I will move on to the quantum spin system. Last 5 times I will talk about quantum spin system. So, I mean, you can talk with the students that if you are not interested in superconductivity but interested in quantum spin system,